Hello friends, in today's question, a thin uniform cylindrical shell closed at both ends is partially filled with water. It is floating vertically in the water in half-submerged state. If rho c is the relative density of the material of the shell with respect to water, then the correct statement is that the shell is, so these are the four options, and we have to find out the correct option or correct statement, that especially with respect to the relative density, and it is being compared with 0.5 and 1 is for 1, and it says that whether that cylindrical shell will be half filled or less than half filled, and that there is a permuted combination of all these options. So we can solve this question by using two methods. First one is purely theoretical. We take each option at a time and try to make analysis based on the relative density is given. And second one is a combination of little bit theoretical and little bit of using the various equations. And that second option can be subdivided into further two parts. Okay, so let's try, you can say, first part, that using the theoretical based. So you can say we can use two methods. And method one is our theoretical approach. And method 2, let us call that, you can say, analytical approach. And the second approach can be further divided into two parts. Okay, and we can discuss them later on. Okay, let us call them A and B. So let us first of all start with our theoretical approach. So first method, which is our theoretical approach. So before going into all the options, there are two key concepts which we should be knowing. First one is that the cylindrical shell is half-submerged state. Okay, so we can say key concepts, and first one is, it is given in the question that the shell is half submerged in water. The shell is half submerged in water. So it means the total water that is being displaced by this half submerged shell will be equal to the weight of the shell plus the water which is put inside the shell and whatever air is inside the shell. Okay, so we can say the shell is half submerged in water, means the total weight of the shell including water inside equals to the water displaced by the half of the displaced by the half of the shell's volume. So this is the first key concept, and second one is rather we can say is an important one, and that is the relative density, which is given to us rho c. So we can say relative density rho c of the material of the shell is compared to water. Is compared to water, and it is crucial in determining how much water is required inside the shell for it to be in equilibrium. Okay, because the important part is that the uniform cylindrical shell is floating vertically in the half submerged state. So for it to be floating vertically especially, it should be in equilibrium. So this relative density is compared to water for determining how much water needs to be inside the shell for it to achieve equilibrium. We are going to keep these two key concepts and make analysis of all these four options one by one. So first option that is given to us is that the shell is more than half filled and rho c is less than 1. Analysis of the option. So we are given option A, which is given more than half filled if rho c is less than 0.5. So this is the first option. So we can draw a conclusion that when rho c is less than 0.5, shell material is much less than the water. Shell material is much less dense than water. So it means if shell is lighter than water, so it means more water is required inside the shell so that the total weight becomes equal to the buoyant force. So which means if shell is very light, more water is needed inside the shell to make the total weight, to make the total weight equal to buoyant force. So this is based on the second key concept, that it should be in vertical equilibrium, and that is only possible when the total weight will be equal to the buoyant force. So as the shell material is much less dense than the water, so more water is required inside the shell. So which means that for the shell to float half submerged, it would need to be more than half filled with water to balance the buoyant force, because shell itself is very light in weight. So it means we can say from here that the shell should be more than half filled. So it means this statement is correct. This statement is correct. Now let us check option B. And which states that more than half filled, but rho c is more than 1. More than half filled if rho c is more than 1.0, sorry. Okay. So it basically means that if we have rho c greater than 1, then shell is more denser than the water. Shell is more denser than water. So it means less amount of water is required inside the shell to compensate for the buoyant force. Means if the shell is itself heavy, then less water, you can say the amount of water needed to achieve half submersion would be less. Because the shell already compensates for the weight. Because shell itself provides significant weight. So from here we can say that the shell would not be more than half filled. The shell would not be more than half filled. So this statement is incorrect. This statement is incorrect. Now let us check statement C, that is option C. It says that half filled if rho C is more than 0.5. Half filled if rho C is more than 0.5. So once again, if rho C is more than 0.5, the material is denser than water, but on the marginal value. So we can say that rho C is greater than 0.5, so which means shell material is heavier than water, but not too much, So there is a possibility that it might be half filled or it might not be half filled. So you can say it is possible, therefore it is possible that shell is half filled with water. So there is a possibility. We are not very sure whether this statement is true or false. So we can draw from here that this statement is plausible. This statement is plausible, but not always guaranteed. Always sure. So we can say this option C might be true or might not be correct. Okay, so this statement might be correct or incorrect. So we are not very sure about this statement. And the important part in this question is that it is only single correct option is there. There is no multi-correct option. Therefore, we already found out that option A is for sure. It's a correct statement. So from there, we can just drive a conclusion that this statement will be an incorrect statement. But based on the discussion, we are not very sure that this statement might be correct or this statement might be incorrect. And let us check option D. We state that less than half filled if rho C is less than 0.5. So this is, you can say, entirely opposite to the statement number A. Okay, the value of rho C is same, but the statement given is just opposite. So from here we can say rho C is less than 0.5, which means that shell is lighter. Shell is lighter than water, so we can say that more water is required to balance the buoyant force. So if it is, you can say, half filled, the total weight will be too less to the shell to be floating as a half submerged. So if shell is less than half filled, the total weight will be, rather you can say would be, too less to cause, or we can say would be too less to balance buoyant force. So we can say this statement is incorrect. This statement is incorrect. So this was purely theoretical based analysis which we made based on the relative density that is given, and now we can shift to the, you can say, second method. And second method we are going to, you can say, divide into two parts. First we are going to consider, you can say, the total weight in the shell, that is water plus air and plus shell, and that will be equal to the total displacement in the half submerged case. And the second part we are going to take all the forces that is acting on the shell. So let us start second method, and we have second method A part. In this case we say that the volume of water in the shell is VW, volume of water in shell is VW, volume of air in the shell is VA, volume of air in shell is VA, and volume of material of the shell is VM. Volume of material in shell is VM. So therefore we can say, let's find out what will be the total weight of the shell. Total weight of the half submerged shell. So you can say total weight of the shell, total weight of the shell is equal to the weight of the submerged part. Weight of the submerged part, which balances the buoyant forces because shell is floating in the vertical condition, because shell is floating in half-submerged state, in a half-submerged state vertically. So it means total weight of the shell is equal to water plus air plus shell. Total weight of shell will be equal to water inside it, air inside it, and the material of the shell. So therefore we can write an equation which gives us that volume of material, of air and water divided by 2, and we have density of water G, and we get this as Vm, and this will be our relative, plus Vw and rho W and multiply by G. We open the bracket and solve it, so we get this as Vm rho Wg plus Va rho Wg plus Vw rho Wg is equal to twice Vm rho C rho Wg plus twice Vw rho Wg. So now it is a simple, you can say, calculation, not. So you can write this as we have rho W in this side and twice this side, so we make some adjustment. We can say this will be equal to Vm rho Wg plus Va rho Wg, and this will be equal to, let me 1 second. Yeah, so we get this as minus twice Vm rho C rho Wg is equal to twice Vw rho Wg minus Vw rho Wg, and we can just solve it now. Sorry, I think it went out of the focus. Yeah, so this will be coming equal to, taking Vmg as common, so we have Vmg and Vmg from here, so we are left with this as Vmg and rho W and rho W. So let me write it first. This will be 1 minus twice rho C, and here we write it rho W. This will be plus Va rho Wg is equal to, and this subtracting this we get rho W, sorry, Vw rho Wg, and G cancel out, rho W cancels out, so we get Vw, that's the volume of water, will be equal to volume of material 1 minus 2 rho C, that's the relative density, and plus Va, that's the volume of the air. Now we are going to carry the entire discussion based on this equation. Therefore, we are given, in the first case, let us take that our rho C is greater than 1 by 2. If rho c is greater than 1 by 2, so obviously 1 minus 2 rho c will be coming as negative. So we can say 1 minus 2 rho c will be coming as negative. So if this is coming as negative, and we have to make sure that this entire equation is balanced, so this first portion is coming as negative, so it means more air will be required. VA should be on the higher side so as to balance this entire equation. So there we can say that VA should be more, that is more air is required. More air is required to maintain the equilibrium. So from here we can say VW will be smaller. So therefore VA is greater than VW. And second, if rho c is less than 1 by 2, so we get 1 minus 2 rho c will be coming as positive. So if this is positive, so now reverse is going to happen, that more water will be required. So it means more water is required for the equilibrium. Therefore VW is greater than VA. So once again we can say that the option number A is the correct option, which states that it should be more than half filled when this rho c is less than 0.5. Okay, and let us do for the second method, part B. We have second method, B part, and here also we are going to get almost same equation, but in a different way. We are going to type it in a different way. So in this case, in the question itself, it is given that we have a cylinder, and that cylinder is half submerged in water. This is level of the water, and L by 2 is the submerged portion, where total length of the cylinder is supposed taken as L, and inside the shell cylinder there is a level of water. Let us suppose that is given as for the height h, that is given as h, and everything is in balanced form because it vertically it is balanced. Okay. So we assume that for a cylindrical shell, Radius is taken as r. Radius is small r and length is equal to L. So we have radius, that is small r. And density of the material is of the shell is rho. Density of material for shell is taken as rho. Mass of the shell is taken as small m. Mass of the shell is taken as small m, and density of water is taken as rho w. Density of water is taken as rho w. So we can write that the mass of the shell in terms of the parameters which are given to us. So from here we can write that mass of the shell, which is given as taken as m, will be equal to pi r square L and multiply by its density. Now we are going to find out all the forces that will be acting on the shell. So mainly there will be two forces acting on it. One will be the buoyant force in the upward direction, and second one will be the weight of the shell acting in downward direction along with the weight of the water that is inside the shell, which will be acting both in. It means the combination of shell as well as water inside the shell will be acting in downward direction, and the buoyant force will be acting in upward direction. And it is given that the shell is in vertical equilibrium. Both the forces will be equal. So we can write that forces acting on the shell. Forces acting on shell. So we are going to have two main forces. First will be the gravitational force on the shell. Gravitational force on the shell, which will be given as mg. M is the mass of the shell, and it is also given that the shell is partially filled with the height given as h. We have taken it h. Shell is partially filled with water to height h. Therefore, the force acting downward because of the water inside that shell water inside the shell exerts force downward which will be equal to pi r square h multiplied by the density of the water and multiplied by g. So total downward force will be the gravitational force on the shell and the total downward force. So therefore we can say total downward force will be equal to mg plus pi r square h rho w multiplied by g. And the next force will be our buoyant force will be acting on upward side. So this is the first, and we have the second main force, which is the buoyant force. and this force is only on the submerged part of the shell. This force is on the submerged part of the shell due to the water displaced. Due to water displaced. And it is given that the cylinder or the shell is vertical and half submerged. So you can, since shell is vertical and half submerged, therefore we can say that the displaced volume of the water thus the displaced volume of water will be equal to pi r square multiplied by L by 2 because it is half submerged. So therefore we can write the buoyant force let us suppose given as FB will be equal to pi r square L by 2 density of water multiplied by G. So we have and total downward force, let us suppose it is given as FT. So we have that it is in equilibrium shell is floating vertically therefore FD will be equal to FB. Downward force will be equal to buoyant force. Substituting the respective equations, we have mg plus pi r square h rho w g is equal to pi r square L by 2 rho w multiplied by g. Now we are going to solve for h. So you can directly write that h will be equal to pi r square L by 2 rho wg minus mg divided by pi r square rho wg, and which can further written as, you can see we can separate the denominator, and that will be coming as L by 2 minus m, and we have this pi r square rho w, and m is the mass of the cylinder or shell. So we already know that, but m is equal to pi r square L multiplied by rho. So substituting value of m in this equation, we get h is equal to L by 2 minus pi r square L rho divided by pi r square, and we have rho w. Pi r square cancels out, and this comes as L by 2 minus L rho divided by rho w. Taking L by 2 common, we get h is equal to L by 2 1 minus 2 rho upon rho w, and we know that relative density of the water will be given as rho upon rho w. So therefore we can get h is equal to L by 2 1 minus 2 rho c. Once again, the only difference in this equation and the previous equation which we found out is of your, you can say, volume of the air. This equation is entirely in the volume form, and that can be converted into respective, the formulas, into height as well as length. The only difference here is our volume of the air. The major equation, the comparative equation, is 1 minus 2 rho c, which is also present here, 1 minus 2 rho c. Therefore, we can write that if rho c is greater than 1 by 2, so h becomes smaller, h becomes smaller, or we can say less water is required, because h is the height of the water inside the shell, so less water is required for equilibrium. And if we say that rho c is less than 1 by 2, so h will be larger, or we can say more water is required. More water is required. Therefore, in every option, or we can say in every analysis, we found out that option number A is correct one. Okay, because we found out when rho c is less than 1 by 2, more water is required. It means it should be more than half filled. So we have option number A is the correct option. Option A is correct. Okay. So there are 3 methods solving the same question. Okay, we can directly go for the analysis based on the assumption, based on the options, and the second part is based on, you can say, analytical, based on 2 separate methods, A and B, and in each case we are going to get the same answer. So this completes the question. Thank you.